Hey everyone. So now, given what we know, we're going to now attempt to solve higher order linear systems that have complex eigenvalues. So, and again, for chapter 6, really all you have to do is apply what you learned in chapter 3 with some intuition about complex eigenvalues and go from there. Really, the hardest part about this is row reduction with complex numbers. Now, some of you may or may not have experience with this. To that, I would tell you the complex conjugate is your friend. What do I mean by that? In that you're going to see in these matrices, you're going to have some elements in the matrix are going to have complex numbers where you may or may not want them, right? Because if you add R1 to R2, actually, let me just write this down to give it substance. Let's say for a 2 by 2, right? If I had 1 and then like minus 3i, and then I had a 3i here and then a 2, as is, no matter what real number multiple of what row I add to one another, there's never going to be a 0, right, anywhere in the matrix. Because if I add whatever multiple of this first row onto the second row, that first element, this element 3i here, it's always going to be added by some multiple of this 1. Therefore, it'll never go to 0 because real and imaginaries aren't going to cancel out that way. So what you do is you multiply rows by complex conjugates to, and this is what I tell my classes, to move the complex number around. Move it to where you want it so that you can manipulate this equation much easier. So, for example here, what you would do is multiply the first row by plus 3i, thus making this first element now 3i, and then you make this element now 9, right? And so then from there, you're in a much better position to try to row reduce. And so just keep that in mind as you do these. Great. Now that I have that aside, this is just like all these problems from here on out, really. Well, actually, this is probably the end. Now, the next section is newer stuff, exclusive to chapter 6. It's really just applying what you already know. And so I'm just running through it for completeness for you guys, and so that everything makes more sense, right? So let's see here. Yeah, I want to go down. Okay, cool. So this is the matrix that I have. As it looks right now, you don't know if it's going to have complex or non-complex eigenvalues. So I'm just going to go ahead and tell you it will. So what you do is always, right, you do determinant of a minus lambda I, right? And so for here, that's minus 2 minus lambda 2, 1 minus 2, 2 minus lambda 2, 2 minus 3 minus 3 minus lambda. And then you pick whatever row or column or diagonal you want to go across and then apply the recursive definition of the determinant. If you have no idea what I'm talking about, that means you skipped a video. So go back to the, 6.3 video and see how I do that in order to arrive at what is the characteristic polynomial for this, which I'll tell you is minus lambda cubed. So assuming you've already done all your determinants, it's minus lambda cubed minus 3 lambda squared minus 4 lambda minus 2. And this is all equal to 0. I'll tell you that, well, this one is pretty easy, right? Because the factors of minus 2 are plus or minus 1, plus or minus 2, and the factors of minus 1 are plus or minus 1. So you have 4 choices for the real eigenvalue here. And so keep in mind, right, when we dealt with 2 by 2 systems, when we had a complex eigenvalue, it was kind of like a multiplicity of 2, right? We didn't have a case where we had a real eigenvalue and a complex eigenvalue, because the complex eigenvalues come in conjugates, right? So for a 3 by 3, you're guaranteed to have, in this class, you're guaranteed to have a real eigenvalue and then a complex conjugate pair, if assuming it has complex eigenvalues. So you're guaranteed from this polynomial that at least minus 1, plus 1, minus 2, or plus 2 are going to be the real eigenvalue from here. And I'll just tell you right now, the eigenvalues for this is minus 1, and then minus 1 plus or minus I. Great. So from there, let's do the easy stuff first. Let's deal with the minus 1. Right. So if lambda is equal to minus 1, then the matrix becomes minus 1, minus 2, 2, 2, 3, minus 3, 1, 2, minus 2. I told you I'd never do this again. 1, 0, 0, 1, 0, 0, 0, 2, minus 1. And then you can row reduce that, or sorry, it's already row reduced. You can try to solve for the eigenvector. And then the top equation tells you, okay, v1 plus 2v2 minus v3 is equal to 0. And then the second one tells you v2 is equal to 0. So that's actually already pretty informative. This already tells me this has to be 0. And then the bottom one tells you that x3 can be whatever. So I'm going to make x3 1, which means that x1 has to be 1. So 1, 0, 1. Great, so that's our first eigenvector. If you remember from the complex eigenvalue video that I made for 2x2, remember, since they're complex conjugates, they share a symmetry such that you only have to worry about one eigenvalue in order to get both of your eventual eigenvectors, right? So now for lambda is equal to minus 1 plus I, this is what the matrix becomes. It becomes minus 1 minus I, minus 2, 2, minus 3, minus 2 minus I, 2, 3 minus I, 2, 1. Now, row reduce this in a way that, look at this, the first column has the complex number like in the first row, and then the second row has it in the second column, and the third row in the third column. As of right now, you have to multiply by complex conjugates in order to do anything, in order to have any chance of row reducing, right? And because this one is especially tedious, I'm just going to go ahead and tell you, after much row reduction, what it comes down to. Okay? So, play with the complex conjugate, try to get it as reduced as you can. If you're successful, you'll arrive at something like this. 1, 0, 0, and then there's a 1, 1, 0, 0, 0, 1 half minus I over 2. Great. So, and then from here, remember, you only get like one eigenvector, right? So I'm just going to call it big V. So the first equation tells you that v1 plus 1 half minus I over 2 v3 is equal to 0. The second one tells you that v2 plus v3 is equal to 0. And then the last one tells you that v3 is free, right? And so something that works here is, I'm going to erase this v and put it over here so that you can see it better, is that v can be, okay, let's think about this. Let's say v3 is 2. So by the second equation, v2 plus v3 equals 0, the v2 has to be minus 2. Okay. And then from there, so I chose 2 because that's going to get rid of the 1 halves and the 1 half minus I over 2. So by that, v1 has to be minus 1 plus I. Right? And you can double check this. And then if you remember, what I told you to do from here is to separate this vector into its real and imaginary parts. So v is really minus 1, minus 2, 2, plus I, 1, 0, 0. Right? So that's fair. From here, remember, if your professor doesn't allow you a crib sheet, which is most professors at Tech for differential equations, you have to set up Euler's formula and now try to find the real part and the imaginary part, right? So let's go ahead and do that. Setting up Euler's formula, and in case you forgot, I really hope you didn't, because this equation right here is very, 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 very important for many things. Engineering, math, physics, everything. Anyway, okay, so as always, it's always e to the lambda t, right? So our lambda was minus 1 plus I. So therefore, e to the minus 1 plus I times t is going to give me e to the minus t, right, times e to the it. E to the it, as per Euler's formula, is just going to be cosine t plus I sine t. Okay, we're in pretty good shape. So now at this point, what you want to do is to try to find the real part of the e lambda t times b. So therefore, the real part, remember I call it x real of t, is going to be the real part of whatever is in here, so e to the minus t times cosine t plus I sine t multiplied onto the vector that we had, right? So that was minus 1, minus 2, 2, plus I, 1, 0, 0. And now remember, I'll whip out the colors, why not, that this part right here is real. It's entirely real. Therefore, it must be multiplied onto this part in order to get something that's real. Something that's not going to vanish when we apply this real operator here. And then, same thing, this is purely imaginary, which we have to multiply by something that's also purely imaginary in order for the real operator to see it. Right? So, let's go ahead and do that. Everything else just goes away, right? The cosine t times the I vector is purely imaginary, so that goes away in the i's of the real operator. And same thing with I sine t times the real vector. So for here, xr of t, so after we apply the real operator, it becomes e minus t for everything, right? That's attached everywhere. And then the red part is going to become minus cosine t minus 2 cosine t 2 cosine t, right? And I'll put this in here. And then remember, I times I shouldn't have to say this with minus 1, right? Minus 1. So minus here, and then this I sine t, or really just sine t at this point, times 1, 0, 0, is going to give me sine t 0, 0. Right? And this is going to be e minus t, and then just these two things together. Minus cosine t minus sine t, and then minus 2 cosine t, and then 2 cosine t. Alright, that's good. And let's do something very similar for the imaginary part, right? So, and remember I like to call this xi of t, and then this is the imaginary operator applied to e minus t. Really the same thing that we had above, but, for completeness and so that, you have a good math education, I'll write it down for you. No worries. Is, again, the v vector, minus 1, minus 2, 2, and then plus I, 1, 0, 0. Right? And then I really should put the brace to close it off. Same thing, right? Let me whip out the colors again. Let's not minimize this. Alright. Oh my god. This pen is kind of finicky. Okay. Should I use different color? Nah, it's fine. Okay, so this real part in the eyes of the imaginary operator has to be multiplied by something that is purely imaginary to be imaginary, right? Therefore, this must be multiplied onto this one in order for this to work. And then this that's imaginary has to be multiplied onto something that's purely real in order for this to work, right? So, now this becomes, I'm going to give myself some more space here. I still want you guys to see it though. Alright, great. This becomes, e minus t does nothing, right? It's attached everywhere. And then this part right here, cosine t onto 1, 0, 0, so that's cosine t 0, 0. And then I sine t onto there. That's just going to be, let's see, plus, put that there. And then that's minus sine t minus 2 sine t, and then 2 sine t. And then really all that is e minus t, and then cosine t minus sine t, right, minus 2 sine t, and then 2 sine t. Right? Good. And then you just add them all up together, right? So the general solution for that matrix is x of t. Don't forget your first eigenvector, that was attached to the real one. So that was c1 e to the minus t times our first eigenvector, 1, 0, 1. And then plus c2, then we have e minus t as well. This was the real one, so this is minus cosine t minus sine t minus 2 cosine t 2 cosine t. And then plus c3 e minus t again. And then minus sine t plus cosine t. Minus 2 sine t. And then 2 sine t. And that's it. So feel free to use the formula in case your professor is there. And yeah.